All right. Well, what we're going to do is we're going to hop right into talking about complex numbers on a complex plane. And we're also going to talk about writing some complex numbers in trigonometric form, all right, in this complex plane. And this is, if you don't know what a complex number is, a complex number is a number which has a real and an imaginary value. So when you talk about a complex number, you probably learned this in Algebra 2 and also pre-calc. And with a complex number, it has a real and an imaginary number associated with it. Okay, and together the reals and imaginaries make up what a complex number is. And normally when we write this, we write it in what's called standard form. Now the standard form of complex number is a plus bi. A plus bi. This is the real, and the bi is the imaginary component of this standard form of a complex number. Now, the thing is that you do not graph complex numbers generally on a normal standard plane. When we talk about a standard plane, I'm talking about an x and a y plane. Okay, that's what we've been doing up to this point. Well, instead, we can graph these in what was called a complex plane. And a complex plane is very similar to a standard x, y, or real plane in that um, we divide it into two different horizontal and vertical axes. However, the horizontal axis is what's known as the real axis. All right, so that's our horizontal. And the imaginary axis is what's known as the vertical axis, or our terms for I. Okay, I for imaginary. So for example, if we were to graph 2, all right, z equaling 2 is our complex number. Well, 2, or negative 2 that is, negative 2 is a real number, so it goes along the real axis, and we would just go 2 units over here, and we plot that point right there. It's on the horizontal real axis at negative 2. If you had a point right here of negative 1 and square root of 3, our point would be negative 1 square root of 3i. And so that is in the real followed by the imaginary root right there. So what we do is we go to negative 1, which is our real, up to the square root of 3 right here, which is our I. So that's where we have our point right there, which is going to be the square root of 3i followed by negative 1 right there. But once again, what you realize that you actually can create a triangle. And what's cool about this is that all these points can be made into triangles. So before we do this, I guess I'll just go through a couple other examples. So if I were to graph negative 7, okay, we'll take another value, and I'll erase this right here. Okay, so if you take negative 7, where would negative 7 go? Well, negative 7 is a real number, so it would go over here. This would be negative 4, and let's just go all the way down here and just say that's negative 7. We would have a point just right there. If we had a point of 5, negative 12i, all right, 5, negative 12i, well, 5 would go 1, 2, 3, 4, 5. Let's say that's 5. And then we go down to negative 12. This would be 1, 2, 3, 4, 5. We'll just say this is negative 12. Okay. And we would have a point right there. Okay. Where we could say z equals 5, negative 12i. And that's what we do for all of those. Okay. Now, the thing is that, like I said before, we can actually, what we create is a triangle. Now, the thing is, can we represent a complex number in trigonometric form? Well, if you realize this, is that, once again, a complex number is made up into a real and an imaginary component. A real and an imaginary component. And for the real, we know the real is in the horizontal, which is kind of like our x. And if you look at our imaginary is in our vertical, which is kind of like our y. And if you recall, back in the day, all right, well, in trigonometry, when we create a triangle right here, and we find an angle, we'll call that angle theta, this point of where we can create this triangle is actually can be broken down into x and y. So in here we have we'll call it BI, and we'll call this A, and then we have this right here, which is our, we'll call it R for our radius coming from, if you're in polar coordinates, coming from a pole up to our point, but we'll call that R for our radius of whatever circle we have. And so right here, if we know that A in this case is -1, in this case, this one right here is the square root of 3I, well, what would this length have to be? Well, we know that R, since it's 1 radical 3 and 2u, using Pythagorean theorem, our R is 2. So can we write this, all right, this equation right here, can we write this as a trigonometric form? Well, how would we do that? Well, what would A be if we want to do this? Well, we know that the horizontal is part of cosine. If we took the cosine of the angle, that's going to be equal to adjacent A over R. A over R. So what does A going to equal? Well, let's put this in, well, in order to solve for A is going to equal R times cosine of theta. And A represents our horizontal component. Okay, well, now let's go try the next one. Let's say I want to do my vertical. Well, we know that sine of the angle is going to equal, all right, in this case, B, all right, when we have BI, I'll just put BI there, I is our coefficient, and then we have R, so sine R times sine of the angle equals BI. And if actually we take this right here, we can actually say that that's going to equal B, and actually I'll get rid of that I right there, that's going to equal B, and then if we want to, we can just put I there, and then we can find out our other component is going to equal BI. So R times sine of theta times I equals BI. Okay, so if we go over here and we put all this stuff together, A equals R cosine of theta. Now this is where you want to write this stuff down, okay? So if you're wondering, and then BI is going to equal plus R sine of theta I. Notice that we have these R's both here, so we can actually factor this out. And when we factor it out, I'm just going to put it right there. And we'll just write that down right here. And so we have then is this is going to equal R times cosine of theta plus sine of theta times I. And that, my friends, is the trigonometric form of a complex number. And that is what we know. So for example, okay, we had to figure out what the angle is, all right, and that will be the form of what we want to figure out. So the question is, how do we figure out this angle? Okay, how do we figure out this angle? Well, in order to figure out the angle is always going to be here, okay? Or once again, we could figure out what that angle is, okay, what that angle is, and using that portion, okay, to help us figure out what this triangle is, this is actually going to be, we have opposite and adjacent, so the tangent. The tangent of angle equals B over A. And so actually the angle we're looking for is going to be the inverse tangent of B over A. And that's how we figure out an angle. So we can put that over here. And so theta is going to equal our tangent, our inverse tangent of B over A. And that's how we can find our angle. All right, well, we found a lot of stuff right here. So our complex number in trigonometric form can be this, all right? And in order to figure that out, we can write this in whatever form we want. So right here, if we wanted to, okay, this is kind of an easier one. I'll erase this. Well, knowing that we have, all right, a very nice and easy problem. So if I want to take this and write it into trigonometric form, first off, I would have to figure out what the angle is. Well, knowing this is 1 and radical 3, we know this is going to be a 60 degrees reference angle. Okay, and so this is going to equal 120 degrees. All right, from here, so we could take this, and knowing this is going to be 2. So our answer in trigonometric form, plug it in here, is that Z is actually also equal to 2, which is R, times cosine of 120 plus sine of 120 times I. And that is our answer. And that would actually equal, if you would go through here, 2 times, just to write it through, cosine of 120, which we know is going to equal negative 1/2, plus sine of 120, which is going to equal square root of 3 over 2I, distributed through, which equals negative 1 plus square root of 3I. And so we just verified that this trigonometric form actually equals our standard form of a complex number. All right, well, that is the introduction of how to use complex numbers on a complex plane, and also how to write the trigonometric form, all right, given a standard form. Okay, and that's what we have right there, and you might want to write that down. All right, there you go. Well, we're going to go through some other problems just a little bit, but write these down in your notes, and yeah, we'll check it out in the next video.